Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so I'm back at the Aleph Class A Amplifier build. Now, this is a 60 watt amplifier, right? 60 watt per side, or monoblock, however you want to do it. Right now, this is my Frankenstein because I'm waiting for proper box to come in, and then I can continue building this. Meanwhile, we need to get the power supply. So, this is the Hiraga, I know I'm butchering his name, sorry, but this is his power supply board or kit, and it came with everything except for the bulk capacitors. So what I want to do today is show you why and how to decide on how many capacitors you need. Okay, now you could just go off and get a module like this, like I picked up just so I could run some amplifiers around here. This is 2 voltage rails, and it has bridge rectifiers, connectors on either end, discharge resistors, LEDs show there's power. It's got everything. It's got 10 millifarad capacitors, 4 on each side. Well, now these capacitors I think are real. They seem to be real. They don't rattle. They feel like they're solid, and they seem to perform. That's the key thing, right? So I think they're real. I don't know, but if you're questioning that, you can get a kit like this, the Hiraga Power Supply. I think they call it Le Monster. It's meant for these Class A amplifiers, but really it's like this. You could use it for all kinds of different things that need power supplies. So today what I'm going to do, we're going to come over here, we're going to look at the current charging and discharging through the capacitor, and we're going to look at the ripple voltage, and we're going to add capacitors to see, to watch how it actually works, okay? Because we have equations, and we're going to look at that real quick too. Because, if you're trying to design it, you just don't want to throw a kitchen sink at it and hope it works. Maybe you want to have a confidence builder that your equations actually correlate with your test data. Alright guys, here, let me just show you this real quick. This is the output schematic, the capacitors of the power supply. It's not complete. I got another video, links below, shows the schematic of this Hiraga power supply board. But this is basically the meaningful part of the output, the capacitor bank. And right now I have installed 1 capacitor on each voltage rail. This is a positive voltage rail, the negative voltage rail. I got plus VR for rail voltage here, minus VR here, and then I show A for amplifier. This is what the amplifier really needs. Okay, in this case, that amplifier board wants plus or minus 34 volts. Okay, so we want plus or minus 34 volts. Well, depending on what my transformer out here puts out, and then it has bridge rectifiers, and then we get the voltage rail, right? What we need to know is that once we start lowering this down and pulling current off of these, how much does this voltage sag, or what's the ripple in between charge cycles? In the US we're 60 hertz, so we get 120 cycles per second, so it's 120 hertz. So with the bridge rectifier it doubles it, right? So we get every 120 hertz we get a charge cycle, and in between that we're still draining current off, so it sags, then it gets charged, sags and charged. So that ripple voltage is the thing that we want to minimize, or we want to make sure that this voltage doesn't drop below that, what's required at the amplifier board. Alright? Power is equal to voltage times current. Now, okay, let's just talk about this for a minute here. This is a 60 watt amplifier, Class A. The good thing about it, a Class A, the bad thing is it's pulling a lot of power all the time. The good thing is it's pretty steady, current flow. It's not like a Class AB where you're going to get very little current and then all of a sudden maybe a lot of current, so you're going to have these dynamic current things. Well, the good thing about those, they're more efficient. They're not pulling all that current all the time. On the negative side, or the challenging side I should say, that they have to provide some dynamic power. In this case we're just supplying a whole bunch of power all the time, and the amplifier can use it to create a sine wave, or it can just burn it up. Either way. So 60 watts, very inefficient for Class A. I think what Nelson Pass is saying for his design is figure about 150 watts. So I know you're maybe guessing 120 because 50%, but it's actually less than that. It's not quite 50%. So I think he said 150 watts. Okay, so there you go. All right, so let's go do a quick calculation and see what we expect. But you know what? I'm going to just kind of cut to the quick here and kind of give you a rule of thumb that I just kind of came up with as I was thinking about this video. If you only want, say, 1 volt of peak-to-peak ripple, okay, 1 volt ripple, for every 1 amp that you're going to have, you need at least 8 millifarads capacitance, probably closer to 10 millifarads. So we're going to see if that holds true. In this case, I think we're going to need close to 5 amps. So, you know, that means 5 times 8. So we need about 40 millifarads. Right about what this guy gives us. Like, wow. Okay, and that's just because we want to hold the ripple to something very small. And the reason why is, here, let me show you the board again with some different stuff on it. I'll be right back. Alright guys, so here's some math, our fun stuff, right? Okay, so what I'm saying is the transformer that I have, it's rated at 25 volts RMS output. Now that's, I think, at 115 volts, which in US we're really 120, but then again we can, you know, go up and down. So I'm probably going to show that I have a little higher voltage, but square root of 2 times that to find the peak voltage is 35.36. We'll see how close to that I actually get. Now I'm also going through some diodes, so I'm going to lose some voltage on the diodes, so maybe that'll balance out. So we'll probably be right around 35 volts. Alright, the rail on the board says it wants 34 volts. Okay, so therefore the peak-to-peak ripple is that 35.36 minus the 34, and it comes out to 1.36 volts peak-to-peak. So a little bit more than 1 volt. Now here's the equation for, this is a really important equation in power electronics, so this is a good one to remember, but it's capacitance is equal to current times the change of time divided by the change of voltage. Okay? For every 1 amp, so imagine this, if you have I is equal to 1, so that basically goes away, right? And a voltage ripple, peak to peak, is 1, then I times this, you know, if I is 1 and change of V is 1, those kind of go away. So capacitance is equal to the change of time, which is, you know, for 60 hertz, 120 hertz, because we're doubling it with the rectifier stage, right? We get about 8.3 milliseconds between peaks. It actually turns out to be a little bit less because we're not charging from, you know, the center of one peak to the center of the next. Anyway, so it's a little bit less, but so that's to our benefit. But let's just say it's 8.3 milliseconds. So that's where I come up with 8.3 microfarads. The time goes away in this equation, right? So we're solving for farads. So 8.3 millifarads. So that's where I come up with, for every 1 volt peak to peak, for 1 amp, you need 8.3 millifarads. Now since we, you know, since we can actually do a little bit more ripple than that, then we don't need as much. If you have 27 volts or something higher on your transformer, you can allow for a higher voltage peak to peak, so you don't need as much capacitance. In this case, I'm kind of limiting myself to 1 volt. Okay, so therefore, for 150 watts divided by the 34 volts on the rail gives 4.4 amps. So therefore, if I need that much capacitance for every 1 amp, then I need 4.4 times 8.3. It comes out to 36.5 millifarads. Pretty darn close to that 40 millifarads. So who knew? Now, turns out I just bought some of these 10 millifarad ELNAs. Somebody asked me if they're real, and as far as I can tell, they feel solid. There's no shaky thing like I've heard some people get when they, it's hard to tell maybe from looks unless you're familiar with them, you used them before. I've used Elnos before, but heck, I don't know. I mean, they look real to me. Looking at their pictures on their website, it looks real, but we'll find out. So I got enough of those to do this, but I also, right now I have these Cornell duplicator caps in here that are a little bit smaller. So we'll start off with those. We're going to start doing some testing to see how close we are to our math, okay? So let's bring the camera over, look at our test setup, and then we'll look at the waveforms here on the Mix-Sig scope and see what the ripple voltage, ripple current looks like, and start adding caps and see where we get. Okay, I'll put 150 watts on this guy, and we'll go, you know, maybe I'll go 50 watts, 100 watts, 150 watts, just show you how the ripple changes, so we can see if it actually follows the equations. All right, okay, let's do it. Okay, guys, let me just go through the setup I have right now. You can see my blast shield. Okay. Looks pretty messy right now. What I have is a differential probe looking at the input voltage coming off the transformer. So we'll see a sine wave coming off of that. Okay. Then all this junk in the middle is some capacitor arrangement I have. What I have is this capacitor right here. I took it off the board, and I have these wires going down to the board, and they're coming up here. And they kind of come up looking like they're kind of close because the pins are flat. And anyway, they're spaced and they're soldered really well, so nothing's going to touch there. And this is just for a temporary, you know, just for this video, so I'm going to be careful about this. But then I have this capacitor that I'll put in parallel. I'll just, right now it's clipped on that wire, I'll clip it onto this and put it in parallel to this capacitor just to show you what putting. Now this is a 6.8 millifarad, so 6800 microfarad, and this is a 10 millifarad or 10,000 microfarad. Okay. This rail right here is just going to be not doing anything. We're going to monitor the output of this rail with a multimeter here. I'll show you that. Here, let me just scan over here. Alright, you see these multimeters. So this guy here, the amp probe, will be looking at the output of this guy, the side we're not using. And also this blue scope, the little blue ring, so channel 2 on the scope. So we'll just, so we won't really see anything happening there. We're just going to verify that nothing is happening. And then on this side that we're going to be looking at, loading down, it's the yellow collar, so it's channel 1, and it has these leads going to the FLIR multimeter, and also the load leads that are kind of wrapped around here going up back this way. So let me show you the load. So we'll be looking at, I'll be looking at, I expect, you can see there's minus 2.3 volts still in there. That is because, and right here there's 0 volts because there's a little load on that one and there's no load on the other one. And the reason there's still voltage there, remember those resistors in that last, well, in the video that I showed where the resistors were 1Ks, they were getting way too hot. So I've removed them and they're all sitting here. So there's nothing discharging the caps right now except for the load I apply. Or, well, there's a little bit of a load up here, the LEDs. So it's slowly discharged. And the meters there will show me when the voltage is on there and when it's not. Then up here, we have the scope, and I have all 4 channels up. So channel 1, like I said, is the channel we're loading down. Channel 2 is the channel we're not touching. And this is, on channel 3 we're going to be looking at the current. Okay, so that's this guy right down here. We'll be looking at current coming in and out of the capacitor. So you can see what the capacitor looks like charging and discharging. And when I put this other one in parallel, you'll see the current going into the 2 capacitors in and out. So charging it, and in between cycles it'll be providing the current to the load. And I've got them all in the center right now. Well, except for the one that has low voltage, it's kind of dropping down. And that's so, well, you'll see. When we capture a waveform, the timing will, it'll be easier to kind of see what's going on if they're all centered, okay? And we have 4 milliseconds per division, so we can capture a number of cycles. This guy right down here is a mixed sig differential probe. That's the amplifier module that these leads are going to right here. Okay, going over to this module. It's on 50X, the lowest setting. And then this guy's the amplifier module for this current probe, the mixed sig. Alrighty. So we're going to zoom in on the scope while I do this. Now, I did use this to bring it up a few times and play around with it. And I also took out the thermistor. So, no inrush current protection. I wanted to take out, once I got confidence everything's working fine, I just plugged it straight into the plug strip over there. The plug strip has a fuse circuit breaker actually, and that's plugged into another circuit breaker. So I've got protection there, plus there's fuses on each output over here, and there's a fuse in this power cord right here. So lots of fuse protection, but I took these impedances out because I don't want to change whatever voltage we're getting from our transformer on our screen. Okay, I want to take out all questionable items, so we just have power coming straight into our transformer, coming into the board. Alright, just takes away some variables. So we're going to zoom in on this screen and see what we see. What I'm going to do is I'm going to flip that switch over here. Sorry, I'm going to flip this switch right here, and then we'll capture waveform. Oh, and let me show you the load. Right up here, I'm going to have this load, got everything else turned off, this load set for 1 amp. So we're going to have a 1 amp load tied. You see the cable coming down behind the scope, wrapping around over here to this output. Alright? So, I hope that makes sense. I'm going to hit the switch. We're going to capture a waveform. We're going to sit there and watch it a few cycles, then we'll freeze the scope and I'll show you what we see. 1 amp load, okay? Okay guys, I'm going to go ahead and flip that switch on. Whoops. Got to get my safety glasses on and reapply the blast shield. Never be too safe, right? Okay, going to hit that switch. There we go. Now, see that channel? Those channels kind of drop into place. That's because they're AC coupled. And when you first hit the switch, it looks, it just throws them out until the AC coupling takes over and centers them. Okay, I'm going to freeze it. Oh, you can't see where I hit the button, but you can see the stop. So that shows you that it's frozen. Alright, let me just spread it out just a little bit. Okay, now the blue waveform, that's the channel we're not touching. So, really nothing there. You can see a little bit of a charge cycle. I mean, there's not much of a load on there. It's not doing much. It's only 100 millivolts per division, so very little movement. Channel 1 is 200 millivolts per division, and you can see this, and look at this, 1.38 volts peak to peak. Hope you can read that. Okay, so that's the yellow waveform. That's the voltage ripple. The green one is that transformer AC voltage at the input with the differential probe. The purple one is the current going in and out of the capacitor. And the way I have it situated, the angle, because it has an arrow on it, right? So down here, this is when the capacitor is putting out current. That's the output. That's negative current because of the way the arrow is pointing into the capacitor. And this plus pulse is the current charging the capacitor. So we had a 1 amp load, and basically, remember from our equation, that would have given us a 1 volt peak to peak, and slightly more than 1 volt peak to peak. And we'll talk about that, okay? Here's what is called the fall time. So see, this is where the capacitor is discharging. The center line, basically where that blue line is the 0 volt or 0 amp. And see, this is 1 amp per division. So it's just about one division down, and it should be because that's 1 amp. So just right about there. The RMS current, if you note, that's 1.639 amps. RMS current is a current going in and out of the capacitor. So it's a little bit more than our 1 amp to our load. Let me just point out a couple things here. Okay, so they're all the zero reference line, they're all on top of the zero reference line, okay? So what you see, if you look at the triangle, what looks like a sawtooth, the voltage ripple, as it drops, and that's where the capacitor is putting out current during this time, and it's dropping, and then right here, the capacitor charges, so it charges the capacitor and the voltage goes back up, but then the purple current drops, so the voltage on the capacitor starts to drain again, and so on. Continues, right? So you can see this green waveform, that's AC voltage coming in, right? So basically, it has to come up to about this point before the current, you know, the voltage at this point here, this is 10 volts per division. So that's 10, 20, 30, you know, around 34, 35 volts, which is the DC voltage on the output over here. And once it rises above that, then it forward biases a diode and lets current flow through. And then current flows up, comes down, and then now the voltage right here has risen up, charged the output capacitors up, the diode starts to turn off, and then as it does, then the purple current drops back down, and you see the voltage here on the capacitor start to drain down, and you see the current drops down here, and then once it crosses the zero line, now the capacitor is putting current out to the load. Now let me bring my cursors up just so I can kind of help make this a little bit easier to see, I think. Okay, so we'll do the vertical bars here, which that's what popped up. Let me grab this vertical bar here. Well, grab the whole waveform. I'm going to put it right there at the peak of that voltage, the yellow waveform. And let me touch the yellow waveform so the cursor goes back to yellow. So right there. And then the other cursor is... Alright, there's the other cursor. I'll just grab and drop it right on the bottom of that spike. So right here, change of X, it says 5.9 milliseconds. Okay, so let me just kind of talk about the timing and how our equation, when we put in that 8.3 milliseconds, isn't quite correct. It's a good approximation, but let's just talk about what's actually happening, okay? So let's just look at the waveform. The green waveform, 60 hertz. So from this point where it crosses zero, comes up and then crosses zero again, going back down again. So from here to here, it repeats. That's a cycle, and that's 60 hertz, and that's about 16.7 milliseconds, something like that, for in the U.S. So if you're 50 hertz, it's going to be what, 20 milliseconds for a cycle. All right. So in my equation, I'm using 60 hertz. So with the bridge rectifier, we get the diodes take all these negative waveforms and they push it up. So we get charge cycles for every waveform. And this AC waveform is converted to a pulsating DC. So the green pulses would be here. Green pulse. And you can see we get a purple charge current on every pulse. Okay, so one pulse is 8.3 milliseconds. It's half the time. And sometimes what you see in people's drawings, let's get a couple more cycles, you'll see, okay, they'll draw like at the top of a voltage waveform, your voltage starts to discharge between one pulse to the next pulse. Now I'm kind of skipping the one in between. So you just draw it from here and come down here. and then it charges up and drops down here. Well, so it's kind of like that, but look a little closer. Now imagine this green pulse right here flipped over, okay? So we'll just start with this green one right here. As a matter of fact, I'll just scroll over here so we can just look at positive green pulses. Well, at least we'll start with one. Okay, so we start up here, and then the voltage rises on this green waveform high enough, you know, so it's above the value whatever stored on the capacitors at that moment. The diode's forward biased, and then the purple waveform turns on, diode conducts and turns, and it pulses this current. Okay, so we're charging, so you see the voltage ripple start to rise. As soon as that purple current pulse happens, then the voltage on the capacitor starts to rise. So our ripple starts, and then right here after dead center, then it's still charging the capacitor, but it's also actually supplying a little bit of current to the load too, right? So it's supplying the current to the load, plus it's charging this capacitor. So we get this big pulse. But if you notice this waveform, you see how the yellow one has a little dimple and then it has a straight line? So that straight line is a capacitor discharging. That little dimple is caused by, here, let me get a cursor line over here just so I can line it up so you can see. So see where that purple current still conducting? So if you notice that purple current, it doesn't just suddenly drop off a sharp edge. It slowly drops off. And that's because as the voltage starts to drop and it starts supplying less current to the diode, keeping the capacitors charged, well, the capacitors are starting to drain too. So as that's happening, the voltage on the diode doesn't instantly get turned off because the capacitor voltage is dropping the same time the voltage on the anode side of the diode is dropping. So you're getting a little bit of current through the diode into the load still, and still charging the capacitor. And then because this cyclic waveform is faster than the discharge time, you see this ramp here, it's pretty slow, that eventually it does reverse bias the diode and it turns off, and that's why you get that little dimple. So it looks kind of sinusoidal there, and then you get that turn off, and then you get the cap discharging. So what that really means is in the equation, you're really getting a little bit longer charge time than that equation accounts for. So what that means is your discharge time is a little bit shorter, and when we put the cursors up there, like if I go right to that side of that dimple right there, because that's really where the capacitor is starting to discharge, and then I grab this guy and go down to the bottom right, that sharp corner before that next pulse happens, you can see it's 5.8 milliseconds. Whoops, 5.8 milliseconds. So the discharge time, instead of being 8.3, it's 5.8. Now if we had a really small capacitor, you know, you're going to see a little bit longer charge time, and the discharge time is going to be less because the capacitor is so small, right? So it kind of makes sense, right? Imagine a really small capacitor, it wouldn't have very much energy to use for the load, so the charge time is going to actually almost look sinusoidal, you know, because your discharge time, as it gets smaller and smaller, sharper and sharper with the smaller and smaller capacitor, then that little dimple is going to drop further and further down before it allows the capacitor to take over. So that might make sense, right? Now what will happen is we put a larger capacitor in here, is going to change the waveform a little bit, because now the commutation of that diode, sharing the current with the capacitor and the diode, is eventually, if we keep on adding large enough capacitors, that's not going to happen. So then we're going to get closer to you know, our equation. Again, the capacitor we have down here is a 6.8 millifarad, not the 8.3 millifarad. And in my equation I said 1 amp, 1 volt which we're just a little bit more than 1 volt. And that's because we got a 6.8 millifarad capacitor. So even though our times are off a little bit, and our capacitor size is down a bit, we're pretty darn close. 1 amp for 1 volt with the 6.8 millifarad cap. So if we did have that 8.3, we would have less than 1 volt. So that was not too bad of a guess. I mean, that was, you know, we're being pretty conservative. Okay, now I'm going to add the 10 millifarad cap to this 6.8 and let's see what happens. Before we do that, one thing I want to point out is the 0 line's right about where that blue line is, and this current is 1 amp per division. So 1, 2, 3, look at that. It's almost 4 amp peak. With a 1 amp load, we almost have 4 amps peak. And what that current does when it peaks up, see, it loads the transformer down, kind of rounds it off. That's why I took out the thermistor, and that's why I took out some of the other things, the variac and stuff in my AC power supply, because I wanted to show that I'm not adding any impedance. My wires are plenty big for this current, I think, but you can see what's happening. Those peak currents, they're causing a little bit of a droop in the voltage. You know what? Before I add the capacitor, let me increase the load. Let's do that. I'm going to increase it to 5 amps. Okay, let's go ahead and turn it on again. Alright guys, turning on the scope, getting ready to trigger. Okay, I think we're all ready to go. Here we go. You'll hear a switch. Okay, let's go and center the image there. Okay, now I'm going to go ahead. We're 1 amp, 2 amps. I'm going to have to drop these guys down so we don't go off the screen. Okay, here we go. 3, 4, 5 amps. Okay, there we go, guys. I'm going to freeze that and we'll take a look at that waveform. It's a little bit more interesting, right? Okay, with a higher load, you see we don't see the little dimple anymore. Now it's a straight sawtooth. But you also see the green waveform. It's a little bit, you know, we got that little rounding there. Now, the current's 5 amps per division, so that's 10, 13 amps peak. That equation I showed was that for every 1 amp we would need an 8.3 millifarad capacitor, right? Since we don't have that, we had about 1 volt peak to peak with the 1 amp. So at 5 amps you would think we'd have 5 volts peak to peak, or a little bit more. But actually it's a little bit less. So our ripple actually got a little bit better. I mean, per amp, right? Okay, so why is that? Well, that's because we have a little bit more charge time. Before we had what, 5.8 milliseconds of discharge time? Let's see where we are now. Let's bring this right to the peak, right where we're starting to discharge. And we'll get this guy right here, right at the bottom of that waveform. So that time right there. Now look, we're at 4.8 milliseconds, so a little bit less time. So that means we're charging a little bit more time. So we end up getting a little bit less ripple because we have more charge time. And that means that the transformer, the winding is supplying more power and the capacitor's providing a little bit less power. So we actually get a little bit less ripple, peak to peak ripple per amp. That's kind of counterintuitive, right? Alright, so for fun, okay, we got 4.7 volts peak to peak. Let's go half of 5 amps load. Let's go to 2.5 amp load and see if we end up with half the ripple voltage. In that equation, if everything else was the same, that would be true. But we know, we can already tell that it's not going to be because the charge time is also changing. Okay, I'm going to go ahead start the triggering again so it's running. Okay, we're going to go ahead and apply the voltage. Get a little beep from the current meter there, I think. Okay, now let's go ahead and that's 1.5, 2.5 amps. So that's half our load right there. Okay, wait until everything settles. Okay, and I'm going to go ahead and freeze it. All right, and turn off the power supply so I can come down here and talk about it. Okay, we had 4.7 and now we're about 2.4. So it's actually, fairly close to half, right? And if you notice, we barely have a dimple. And so I think our time is kind of working more linearly right now. As we drop our current, we're going to end up getting that little ripple on that discharge waveform. And that's when our time actually changes a little bit for us. So right here, we're getting a little bit more ripple per amp than we did at the lower one. Whoops. Here, let me get these things lined up here. And right down here at the bottom. And that's 5.48. So it's discharging a little bit longer. So we have a little bit less charge current right here. So it's interesting how that works, right? In my equation I had 1 volt per 1 amp and with an 8.3 millifarad capacitor, and at the 1 amp we got pretty close to that. It was off a little bit, and it was because the wave shape was kind of deformed because of the timing and everything, so we had that little dimple. But at this point we're just barely starting to see the dimple, and it's still pretty much a sharp, sawtooth. And so we have 2.5 amps and we're 2.4 volts peak to peak. So yeah, I think our equation got us right there in the neighborhood. Okay guys, so now what I have is I have the second capacitor in parallel, the 10 millifarad cap. So I'm going to start the scope again, and we're going to do the 2.5 amp. We're going to start with the 2.5 amp situation. So we're going to see how this compares, okay? So right now we got 2.4. Now I have a 6.8 millifarad cap and I'm adding a 10 millifarad, so it's a little bit more than double. So if our equation holds true, then this voltage should drop at least in half. So our peak to peak should drop down to 1.2 volts peak to peak. Okay, let's see what we get. Okay, let me turn it on. Okay, little inrush current there, and there's 1.5, there's 2.5 right there. Okay, let it settle down a little bit. Okay, I'll freeze it, and I'll drop our load and turn it off. All right, look at that, 1.2, so it dropped just about in half. Now, it wasn't quite linear. We would have thought it would have dropped a little bit more than half because we added a little bit more than twice capacitance. But you see how we're getting that dimple back again? That's because our capacitor is actually, plenty big for our load, and so we're getting a little bit longer charge cycle and a little bit less discharge time. So that what it does is actually gives us a little bit higher ripple, which is kind of interesting, right? All right, we're going to go back to the 1 amp, okay? Okay, we're going to try the 1 amp, and then we'll go to 5 amps, okay? All right, here goes. Turn on the scope, hit the switch, and we're set up for 1 amp. Oops. All right, and there's our 1 amp. Okay, I'll do the same thing. I'll freeze it, turn it off. Now, look, we drop down to 0.7, so about half. So you can kind of see it's fairly linear. And you can see the little dimple thing there. So if I adjust this current to, whoops, I can just do it that way. If I go 1 amp per division, see it's 1 amp down here for the load, and then it's about 5 amps peak. 1, 2, 3, about 4.5 or something. So now let's go to 5 amps. So I'm going to have to drop this back down. Okay, let's do that 5 amp load. Okay, here's the 5 amp load. Let me start the scope again. Turn on the power. There's 1 amp. I'm going to crank it back up. Okay, and there's 5 amps. Let it settle out. I'll freeze it right there. turn off the power supply. Okay, so this ripple, the peak-to-peak ripple, is about the same as the single capacitor at a 2.5 amps, right? So now we're at 5 amps, double the size of the capacitor, and so essentially dropped our ripple in half. So again, here if I get my cursor over here, you see the cursor here, I'll turn it, get it tied to the yellow markers there. See the purple waveform right here? The purple waveform turns on and it's charging the cap. So you see a sharp turn right there, right? It's charging up. See the purple's at the peak right there, still charging. And now we're at the peak here. And so now it's dropping off. So you think that the capacitor's doing all this, but it's not. The purple one is still on, so it's sharing with the capacitor. It's sharing, still sharing. Then right there, the diode's turned off. And so now the wave shape changes and it gets sharp. So from that point to right there is where, let's see, what is that? 4.6 milliseconds. So that's 4.6 milliseconds discharge. So with the larger capacitor, we even have less discharge time. So, so that's one thing to keep in mind. The larger the capacitor you have for the specific load, the less of a shark tooth you get. You get a little bit longer diode commutation before it turns off and you get just discharge from the capacitor. So your discharge from the capacitor actually turns out to be a little less time. Hey guys, was that helpful? Did that make sense? Let me kind of try to sum it up here if I can. Now I showed all these equations, right? And what I was saying is you can kind of approximate how much capacitance you need by looking at this formula for a capacitor. The discharge, how much capacitance you need for discharging. So change of voltage, if you say it's 1 volt peak to peak, and you start with say 1 amp, then those things go away and you end up with change of time, your discharge time. And I was saying, well, here in the US, 8.3 milliseconds is half a cycle. So if we're discharging half cycle, charging half cycle, that was just a rough place to start. Well, if you do that, you're going to be pretty conservative, because now capacitors, they could be a 20% tolerance on a capacitor, and temperature and aging and stuff, so it's good to be somewhat conservative. And so I was saying, okay, 8.3 millifarads per amp per 1 volt. So if you want half a volt, you need twice that much capacitance. If you have twice that much current, you need twice that much capacitance. If you have say 2 amps plus, you only want half a volt. Now that's 4 times, because you're dropping your voltage by twice and increasing the current by twice. So then you'd go 4 times that. Well, so that's kind of the approximation that I was coming up with this. But to get a little bit more accurate, you could go back to the waveform and you say, okay, sinusoidal waveform would look like this. Now, but the negative pulse gets thrown up here, so you get a charge cycle for every one. The red here's the current. Purple voltage is doing this, and the black output on the capacitors might look like this: a discharge, hit a cycle, charge, because you get current charging, discharge, current charging, discharge, so on, right? But you can see, even if now maybe it's more obvious when you look at this picture. Let's say it starts to discharge at the peak of the waveform, which it doesn't, right? It actually starts to drop with the voltage, because the diode will still be on commutating, providing current as it's dropping. And then as this waveform gets steeper than this discharge line, then they separate, and that's what causes that little nipple at the top, that little bump, right? So what that does though is it shortens this discharge time, how much time your capacitors actually have to hold up per cycle. That helps this equation become more conservative. I'll tell you what the number I usually use to approximate is actually 6 milliseconds, because you know, you can, if you're being too conservative, you can end up with, especially if you say 4, you know, once you start multiplying this, your conservative factor gets multiplied too, and so you can end up with a lot more capacitance than you really need. So anyway, I hope that kind of helped make sense of all this stuff. I know, you know, it's a whole video just to talk about capacitors and charging and stuff, but and maybe it even needs more time, but and you know, I'll go ahead and install those capacitors, and we'll get back to our amplifier build. Okay, so hey guys, I want to thank my patrons as always. I really appreciate their support. I think it's just amazing, and I want to say thank you to everybody for watching videos and supporting the channel and your comments and all that. And I've got lots of videos I want to do. I just wish I had more time. But yeah, I got to work too. So anyway, thanks for everybody watching everything, and you can become a patron for as little as $1 a month. But here we go, guys. Bench is full of stuff. We'll see you next video.